Hi, welcome to our 29th lecture in Graduate Combinatorics. Today we'll continue our discussion about trees, and we'll talk about a topic involving the notion of minimum weight spanning trees. So to describe this notion and the problems associated with it, I need some definitions. So first, I will define a notion of a weighted graph. So a weighted graph consists of two things: a graph gamma, which is undirected and simple, vertex set V and edge set E, and consists of a weight function or cost function, which associates to each edge a weight, which can be any number from 0 to plus infinity, the weight or the cost of the edge E. You can think of having a communication network, and the weight of the function will be the cost of building a road between them or something like that. Now, the weight of the graph gamma is the sum of the weights of its edges. And the problem that we're interested in is the following: giving a connected weighted graph gamma with weight function W, find a connected subgraph of it that has minimum weight. Now, this problem, so let's make some observation about this problem. You could have the situation in which the graph gamma is the complete graph Kn. And well, before we go to that, first, because the graph gamma is connected, that implies that we're looking for a connected subgraph of it of minimum weight, and the weights are non-negative. Minimum weight subgraph has to be a tree, because if you contain some cycle, then so if you don't have so the weights are just on the edges, and so let's put the weights here to be at least greater than 0. If you have various weights on these edges, let's say W1, W2, W3, W4, W5, then you can take the largest of these weights, and you can, let's say it's W3, and you can delete it, and you would obtain a subgraph that is still connected because you deleted an edge from the cycle, so you can still get around anywhere in the graph, but the weight of the new subgraph is smaller than the weight of the previous subgraph. Okay, so I guess this is first observation 1. Now, okay, so this kind of motivates the notion that which is contained in the title. We talk about minimum weight spanning trees. So here, when we're talking about finding a connected subgraph, we are looking at essentially finding a tree of minimum weight. Now, okay, so that should make the problem easier. Well, let's consider the graph, like I mentioned earlier, gamma equal Kn, and let's say all the weights, you have all these weights positive. So all the weights of every edge, it could be positive. Okay, weights of all the edges are positive. Then how many trees are we looking for? Well, we have to find out the minimum weight of all the spanning trees of Kn, and we know that there are n to the n-2 spanning trees of Kn. And simply just listing them and trying to compare their weights, it's not feasible for larger n. So one has to do something better. So again, with this observation in mind, if we have gamma W a weighted graph, weighted connected graph, then a spanning tree, let's call it T star of gamma, gamma is called a minimum weight spanning tree. Sometimes it's abbreviated MWST, but most time minimum spanning tree of gamma if the weight of T star is less than or equal than the weight of T for any spanning tree T of gamma. So essentially the weight of WT star is the minimum of all the weights the spanning trees of gamma. Now I call it a minimum weight spanning tree because it doesn't have to be unique. Just think the simplest example would be if you have the complete graph as before, and the weights of all the edges are the same, then any spanning tree in that situation will be a minimum weight spanning tree. So there are actually quite many minimum weight spanning trees in that situation. Okay. Now let's describe an example. So let me draw an example from our notes of a graph. Let's say we have the vertices A, B, I avoid using D and E, so I have X and Y. We have these edges and the weights. Color 3, 4. 7, 6, 9, 10, 11. Okay. So the graph is in the picture. You have a graph on 5 vertices, and the weights are drawn on the picture as well. And you can think of this. So we have this matrix. So you can think of a weight matrix associated to the, let's call it W. It's a graph in which we put the rows A, B, C, X, Y, and the columns also A, B, C, X, Y. Okay. Now when A is not adjacent to A, so we put a 0. So we put zeros on the diagonal. Now, wherever we have edges and their weights, we put them there. So you have 3, 11, 8. So this matrix is symmetric. 7. But you notice that we don't have an edge between C and X. So in that situation, we say we put infinity. If you were to implement this, you would put like something, the largest possible weight that your computer would allow you. So so you put something very large in that situation. So whenever you don't have an edge, that you can put this in the matrix as associating at a very high weight. Okay. So this is the weight matrix, and again the problem is how to pick. So in this case we have 5 vertices, so we want a spanning tree. So we want to pick 4 edges that they form a tree, and together they have the minimum weight. So I will give you the now what is called Kruskal's algorithm. So we'll run it first. I'll explain how it works on this example, and then after that, it shouldn't be too difficult to understand how it works in general. And we'll explain why it actually does what it's supposed to do to construct a minimum, produce a minimum weight spanning tree. Okay. So what does it do? Well, in the first step, pick an edge of smallest weight. Let's call it E1. Okay. It says an edge because there could be several that have smallest weight. So you just have to, you pick one of them. Again, this algorithm is not going to produce necessarily, it doesn't produce all minimum weight spanning trees, it produces one of them. So in our situation, in the first step, we pick the edge AB. Okay, it has the weight 3. If you look, 3 is the smallest. So here. Okay. In the second step, so this is, you do this procedure n-1 times because you want to pick n-1 edges. So in the second step, you pick an edge E2 of smallest weight in E minus E1. So in the first 2 steps, there's not much problem, but so which one is this one? This one will be BC. 4. That's the second one. And then from the third step and on, you have to be careful. So now you have 2 edges. Pick an edge E3 from E minus E1 to that doesn't form a cycle with E1, E2, and has smallest weight. So this is an example of a greedy algorithm. You do kind of what common sense tells you to do. You pick one edge at a time, such that you have the smallest. You don't create cycles. So, and then you pick the smallest possible weight that you could have. So in our situation, if we just had smallest weight, then the candidate is the edge AC, but you see that one has weight. That one creates because that has a weight 5, but this one cannot be chosen because it creates a cycle with AB and BC. So 5 is forbidden, and then what is left? We can choose the edge 6, which is the edge between X and Y. That one is okay. Okay. So like I said, this procedure continues like this until the end. Let me finish it on this example on this page before giving the general description on the next page. So the last edge to be chosen here. So we have chosen 3 edges, and now we just need one more, and the last one will be, it has weight 7, and is this edge here between B and Y. And so we get a minimum, we get a tree whose weight is 7 plus 7 is 20. And we'll prove in a second that this is actually a minimum weight spanning tree. And in this situation, it's unique. But that may not be the case in general. Now, coming back to the description of the algorithm in general, Like I said, it goes on like this, and in the step n-1, pick an edge e n-1 in e minus the previous edges that does create a cycle has smallest weight. And now the result that we want to prove, so proposition or essentially theorem, is that the previous algorithm produces minimum weight spanning tree. Now, one part of this proposition, it's easy. It's the part about the spanning tree. Well, the resulting subgraph, so the subgraph consists of this n-1. So in case it's not clear, so let's put output here. Subgraph gamma with edges e1, e n-1. So we just pick the edges, and then we take the whole vertex set. Yeah. So the resulting subgraph, so the resulting subgraph from this algorithm has n vertices, n-1 edges, and no cycles. It has n vertices because we will let this subgraph have n vertices. We choose n-1 edges, and we choose them such that they do not create cycles, so there's no cycle. So therefore, it must be a tree. So let's give it a name. So the resulting subgraph, let's call it T. Okay. Now, what do we want to prove? We want to prove that T has minimum weight. So to do that, let's consider T star a minimum weight spanning tree of gamma. So what I want to show, so claim, is that the weight of T, which comes from the algorithm, equals the weight of T star, which is a minimum weight spanning tree. So that would finish the proof. Now, to prove that, well, we have, here's how it works. It's a bit of a small case analysis. If T equals T star, then we are done. But again, they have the same weights, and that's it. If not, so in T, we have this order in which we select the edges. We pick the first edges, one of minimum weight, second edge, next available of minimum weight, and so on. So if that gives us a tree T. Now the tree T star has some set of edges. And in the situation that T and T star are not actually the same trees, there's going to be an edge. Let's call it AJ, EJ, be the first edge chosen by the algorithm in T, in the step J, that is not contained in T star. Okay. Now, so T star doesn't contain EJ. So then when you add EJ to T star, will create creates a unique cycle. Okay. So let me. This is one of them. Okay, so let's say this is my tree T. Don't worry about the weights for now. I just wrote this is T star. And let's say this is EJ here. Okay, so you see there are some edges that T and T star have in common. There are two edges that they have in common, but they have two edges where they differ. And so you see that when you add this edge EJ here, it creates this this triangle with two of the blue edges. Okay. Now, okay, so we have this cycle that I mentioned here. It creates a unique cycle in T star union EJ. And this is this unique cycle here, C. Okay. Now, this cycle C has EJ. You see, like if you look at these three edges in the cycle C on the right, they're two blue, and you added now we added this this EJ edge, so we created a cycle. If we look now on the picture on the left, the tree T, if you look at these three vertices that are involved, there is not all of them, not all the edges. So let me write it here, because T is acyclic. Not all the edges of C are in T. Okay, C for us is this triangle with two blue edges and one black edge, EJ. And if you look on the left, yeah, there is this edge, this pair here, which is adjacent in T star, but is not adjacent in T. There's no edge here. Okay, so that's exactly what I'm going to say. There exists, let's say, E prime J in C, such that E prime J does not belong to ET. So this would be E prime J here. Okay. All right. Okay. Now, what do you do next? So we have this, the trees are the same up to the edge EJ, and now you have this EJ and EJ prime. So let's look a little bit and try to understand what's the connection between the weights of EJ and EJ prime. So the trees, so if we have so T star, the tree on the left, the tree T star contains E1 blah 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 EJ minus 1 and E prime J. So we can say that maybe this one is E1 here. This one is E1. Blah, blah, blah. There's maybe some more edges through there. And this one is EJ minus 1. You can think of it this way, EJ minus 1. Maybe the trees. It's bigger. And now this, like we said earlier, the step J is where we have an edge that belongs to T, but is not in T star. But up to that point, the tree T star contains E1, E2, EJ minus 1. And it also contains this edge E prime J. Okay. So T star contains all edges, chosen in the first J minus 1 steps by the algorithm. Okay, so let's put it here. Let me write it this way. The tree T contains and makes a choice for EJ. So at that step, in step J of the algorithm, both edges EJ and E prime J are available. And they're both legit because we know that T star contains E1, EJ minus 1, and E prime J, so there's no cycle between them. And T, chooses EJ, so there are no cycles there. But the algorithm chooses EJ, okay? So because it chooses EJ, it must be that the weight of EJ is less than or equal than the weight of E prime J. Okay? If the weight of EJ was higher, was because otherwise, if the weight of EJ was strictly greater than the weight of E prime J, then the algorithm would have been better off. We would have chosen E prime J instead of EJ. Okay. All right. So we get this relation. Now, what we do is we look at this tree, T star, and we make another tree out of it. Let me see if I can do something here. Lasso this, move it a bit this way. Oh, brilliant. Okay. And now let's make another tree here. There's a different color. Purple. So we do here T star. And what we do is we add EJ and we subtract. So let me T star. Oops. Union EJ minus EJ prime. Okay, so what tree is this? So everything before stays the same, E1, EJ minus 1. This part stays the same. But now here, what we do, we added EJ, so this edge comes in, and the other edge disappears. So EJ comes in, and the other edge disappears. So this new tree has more in common with T than the previous tree. So you should notice that the tree, well, first of all, so consider subgraph. Let's call it T star star, which is T star union EJ minus E prime J. Now it has n vertices and minus 1 edges, and you can prove that is connected or acyclic. I leave it to you to figure out how that works. It's not difficult. And so it's a tree. Therefore, T star star is a tree. Now, what can we say about its weight? So the weight of T star star, it's the weight of T star, we added ej, so plus the weight of ej minus the weight of e prime j. But the weight of ej is less than or equal than the weight of e prime j. So this quantity here is less than or equal to 0. So this is less than or equal than wt star. Well, how can it be? Well, T star was the tree of minimum weight. So the only way that this happens, this must imply that we must have equality here. So actually the weight of EJ equals the weight of E prime J. Okay, so then what do we do? Well, what we found is it means that T star, T star star is a minimum spanning tree, but it agrees with the tree that is produced by the algorithm, not only on the first j minus 1 edges, but it agrees on the first j edges. And then we can go back to our initial step here. We ask if our tree is the same as T star star, then we are done. Otherwise, it's not going to be EJ, which is the first edge chosen in T that's not in T star star. It's going to be a later edge, and we can repeat the algorithm. At the end, we can show that the weight of T, I mean, equals the same. It's the same weight as the T star star star, which is will be a minimum, the weight of a minimum weight spanning tree. Okay. So yeah, this is the Kruskal algorithm. It's very efficient. It runs fast. There is a similar algorithm which is called Prim's algorithm, which picks vertices instead of edges. So it's similar. It's also a greedy algorithm, but we won't discuss it here. What I want to make you aware of are these properties, some properties that we used here. These are sometimes called exchange properties, and they appear in various realms, in the realms of spanning trees, but they appear in the realms of linear algebra when you talk about the bases and so on, and in general setting of the realm of what I call matrices. And here's how. So the one that we use. So these are, I listed them exercises. So you have two type of properties. Let's say one. Let's say you have T and T prime be two distinct trees. So distinct trees means edge sets not the same on the same vertex set. Let's say V. Okay. Then what is true is, so, well, let me state it this way. So this is a common scenario. Then you have two situations. For every edge E that one has and the other doesn't. So for every edge E in T that is not in T prime, there exists an edge E prime in T prime minus T, such that if we remove E from T, we disconnect it, but then when we add E prime, connect it again, and this is a tree. So that's the first one. And the second one looks similar, but it's not the same thing. And this is the second one that we used a bit earlier, is that for any edge E, okay, let me look, yeah, E, let's say it this way, E prime in T prime minus T, there exists E, the edge in T minus T prime, such that if I take T and I add this extra edge in it, I create a unique cycle, but that cycle cannot be, not all the edges in it can be in T. So there is an edge from T that I can remove, such that the remaining thing is a tree. Okay. So these are exchange properties for trees on the same set of vertices. And yeah, they're not too difficult to prove. And I think I gave the solution in the notes in, I think, in some previous material from previous years, but you should try to prove it yourself as well. So now let's move on from the trees. So let's talk a little bit about graphs and some other matrices and eigenvalues. So we've seen the Laplacian matrix, and when we talked about it, we mentioned the adjacency matrix. So if you have a graph, gamma, we can associate A, sometimes A of gamma, adjacency matrix. This is a V times V matrix with the rows and columns indexed by the vertices of the graph, where A of xy equals the number of edges between x and y. And this notion can be defined for general graphs with loops and with multiple edges, but most of the graphs I will talk about are simple, so we'll just assume simple. Now let's do some examples. So let's say I have the following graph. So I have its vertices labeled 1, 2, 3, 4. So let's say this is gamma. And let's say I have another graph here, gamma prime, which looks very similar, but the labeling is different. 1, 2, 4, 3. Okay. Now, when the way I define the adjacency matrix in this situation, let's say we label the vertices 1, 2, 3, 4. Okay, and that's how we write the rows and the columns. We have 0, 0, 1, 0. Then 2 is adjacent to 3 and 4, so you have this. 3 is adjacent to everybody. And so this is the adjacency matrix of gamma. And the adjacency matrix of gamma prime, same labeling, we have 1 is adjacent to 2 and 4. 2 is adjacent to 1 and 4. 3 is adjacent just to 4, and 4 is adjacent to everybody. Now, what you notice is that the two clearly gamma is isomorphic. I don't think we use this notion, but this symbol. But the gamma and gamma prime are isomorphic. Okay, you can map. See the mapping. You can map 1, 2, 3, 4. You can map them this way, and you can map 1 to 3. You can map 3 to 4, and then the other ones you can do. You can do 2 to 2, and 4 to 1 if you want, or the other way around. Okay. So the graphs are isomorphic, but the adjacency matrices with these labelings are not the same, clearly. So A gamma is clearly not the same as A gamma prime. So sometimes the notion is here can associate an, or if you don't use an and use the adjacency matrix, you assume that you have some kind of ordering on the, or like you have a way of listing your vertices that you have in mind when you write the matrix. So it's not just I label the vertices 1, 2, 3 to n, but I actually, when I list them as rows as column, I list them in that order, 1, 2, 3, and not in any other permutation of that. Okay. So that's one thing about the adjacency matrix that you have to be a bit careful. But what happens is that, so I described this in the notes. What you have is that there is a relation between adjacency matrices of isomorphic graphs, and this is I guess we can list it as a theorem. So let gamma and gamma prime be two graphs with the same vertex set, let's say n. Now, one thing I had to do before this, I would rather show it to you on this example how it works. I think we mapped 2 here. I think in the example I mapped 2 to 1 and 4 to 2. All right. So we have this permutation sigma. So what I wanted to, before I give you the general result, if you have a permutation sigma in Sn, you can associate to it what is called a permutation matrix, P sigma, where the easiest way to remember is that the lth column of P equals, so we have our canonical base vector E0, E1, E2. You have EJ, where the 1 is in the J position, and En, this one is in the N position. So permutation matrix, the lth column of P equals E sigma L. Okay, so I give you as an example there that if for the permutation that's involved in our previous example, this one here, 1, 2, 3, 4 going to 3, 1, 4, 2, 2, the permutation associated with P of sigma, you have 1 gets mapped to 3, so the first column is going to be E3, which is this one. Then 2 is mapped to 1, so the second column is this one. 3 gets mapped to 4, so you get 4, and then this is the same thing as saying that, so it's P, or P sigma, it's a 0, 1 matrix where there is exactly one in each row in each column, and that 1 is obtained like this, P sigma L, and L is 1. Okay, so that's what the permutation matrix is. And with that in mind, the result that I want to state is that if gamma and gamma prime are two graphs with the same vertex set n, then the graphs gamma and gamma prime are isomorphic if and only if there exists a permutation matrix P such that the adjacency matrix of 1, let's say gamma prime, equals P inverse times A gamma times P, but for permutation matrices, the inverse is the same as the transpose, is P transpose A gamma times P. Okay, so two graphs are isomorphic if and only if they're similar, but they're similar not just by any matrix, they're similar by a permutation matrix. Okay, now how does this work? Let me give you quickly the gist of it, of this result. So let me do it again with the example that we have here in mind, this example. So let me draw it quickly here. So you have 1, 2, 4. This is gamma. And the permutation sigma. Okay. Now, one thing it's clear is that the sigma is an isomorphism from gamma to gamma prime. Okay, because you map, so I think that's pretty clear because it maps 1 to 3, maps 3 to 4 here. So you have edge between 1, 3, even only if you have edge between 3 and 4. And then you map 3, no, this 3 wasn't mapped there. Mess it up just 3, 1, 4, 2. Sorry, this is the wrong one here. 3, 1. 3, 1, 4, 2. So 1 goes to 3, that's okay, but 3 has to go to 4. It's okay. And then 2 goes to 1, and 4 goes to 2. And you can check that you have edges between pairs of black vertices, if and only if you have edges between the corresponding blue vertices. Now, P sigma, as I mentioned before, the matrix P sigma has the property that its Lth column. So if you multiply a matrix by this L canonical vector, you get the L column. That L column equals E sigma L. That's for any L. And now, so what I want to show is I want to show this relation between these two matrices. Now, what I have is that in the graph on the left, J is adjacent to L, if and only if the corresponding vertices on the right, sigma J, is adjacent to sigma L. Now, these facts imply that they're actually equivalent to the fact that the adjacency matrix of gamma, A of gamma between J of L, actually equals the adjacency matrix of gamma prime between sigma J and sigma L. Because if one of the entries is 0, then the other one is 0, and if one of the entries is 1, then the other is 1. Okay. So this is from being isomorphic. It's equivalent to this property, which is actually equivalent to this property. Okay. So now what we're trying to get here is the relation between A gamma and A gamma prime. So AJL is the entry in the row J and column L, and that one is obtained by multiplying the transpose. So you multiply to the left by EJ transpose, A gamma, I put A gamma here at the, so for me, A gamma, it's the same thing as like this, and A gamma prime, it's the same thing as A gamma prime. So this is this expression, and over here we have something similar. We have E sigma J transpose A gamma prime, E sigma L. Okay, so these two things are the same for any J and L. But what is E sigma J and E sigma L? You see, E sigma L has this expression in terms of P, and that's here what I meant to do is multiplication. So that's P sigma times EL. So if you replace it over here, you get P times EJ transpose A gamma, and here you get P times EL. And when you unpack it, you get EJ transpose, and inside is going to be P transpose A gamma P and EL on the other side. And now, what does it mean? You have that the JL entry of this matrix equals the JL entry of this matrix. This is gamma prime. And then from there, it means that these two matrices must be equal. So that implies that means that A gamma has to equal P transpose A gamma prime P. And if you unpack it the other way around, you get the result that we wanted. Okay, maybe it's not the same order, but you can, yeah, you get it's actually the result here. Because this result is actually equivalent to switch the order. A gamma equals some permutation matrix, maybe not the same as P, but if you right, it is A gamma equals P transpose A gamma prime. No, it's P times A gamma prime times P transpose, which is P A gamma prime times P, something like that. Okay. So the main point here is that the adjacency matrices for isomorphic graphs, no matter how you label the vertices, are going to be similar by permutation matrices. That doesn't help recognize graphs when they're isomorphic because you're looking for, their n factorial permutation matrices. So it's a bit tricky to go through all of them. So that doesn't work. But it has another consequence. It states that all these adjacency matrices are going to have the same eigenvalues because similar matrices have the same eigenvalues. So starting with the next lecture, we'll describe some properties of these eigenvalues and how they relate to properties of the graph.